Hi. So today we are going to be presenting and analyzing the work of Martina Lippi and Alessandro Marino, who published a paper titled A Mixed Integer Linear Programming Formulation for Human Multi-Robot Task Allocation at the IEEE International Workshop on Robot and Human Communication.
So why HRC? Human-robot collaboration provides the following benefits, specifically high reconfigurability, extreme flexibility, and also the ease of changing the task execution while maintaining high efficiency. As we all know, the addition of humans with robots working in factories or industries always helps us in increasing the flexibility and making the process more modular and more granular, aiding in high reconfigurability as well as adaptation and altering of tasks while still maintaining high efficiency. So what exactly are human beings good at? We are good at reasoning and dexterous manipulation, whereas robots are good at endurance and strength. And we're trying to combine the best of two worlds in HRC. So the factors affecting the distribution of tasks usually include fatigue, overall completion time, precedence of tasks, various time-dependent and spatio-temporal constraints and factors. So even whenever in industrial settings, human beings and robots need to collaborate, and we're trying to allocate specific tasks to specific agents, whether it's human beings or robots. Fatigue, overall completion time, precedence, and spatiotemporal factors all equally play an important role and a very important determinant in choosing the right person to perform a specific task. So this work basically talks about or focuses on multi-manipulators collaborating with multiple human beings, where the robots can perform tasks by themselves or in tight collaboration with other robots. Human beings can perform the tasks directly as well, but in addition to that, they can also supervise the robots which are performing tasks in collaboration with other robots or by themselves. And the supervision by human beings guarantees a minimum accuracy in the task completion.
Task allocation and scheduling for multi-robot as well as for human-robot teams are very important problems with applications to manufacturing, warehouse automation, and pickup and delivery. Human robot and multi robot task allocation share many common points and methodologies, but also have inherent differences due to the peculiarities of the human agent. So, the main problem to solve is how can the overall time required to execute a task be minimized while optimizing the work quality and balancing human and robotic workload? There has been a lot of previous work that explores this problem. Let's go over the novelties that this particular paper presents. With respect to previous works, the following novelties are introduced. Number one, the offline task allocation takes into account several features and constraints simultaneously, like time and spatial constraints and workplace limitations. It allows the assignment of more than one agent to work on the same task. Moreover, the concept of human supervision is introduced in order to increase the quality of task execution. Second is a closed-loop rescheduling framework, and it is devised based on real-time monitoring of the parameter's performance. It is able to adapt to dynamic and stochastic agent parameters.
Now we're going to set up the problem statement and try to figure out how the optimization problem is set up for the industrial setting with robots and humans collaborating with each other. We basically have, in this setting, we have a list of agents going from A1 to ANA, where NA is the cardinality of the number of agents, and here an agent could either be a human being or a robot. So as we can see, if we split up these set of agents into two different parts or two different sets, we get AH, which represents the set of human agents, and AR, which represents the set of robotic agents. where NH is the cardinality of the human agents and NR is the cardinality of the robot agents, respectively. So they both, the union of both of these sets gives us the entire agent set A. And let's assume that in this specific industrial setting, we have a set of tasks T, which contains tasks T1 to Tm, where m is the cardinality of the number of tasks. So the cardinality here refers to the exact number of the specific like parameter, whether it's number of agents or number of tasks. So the PIK is a very important variable which basically is introduced to represent the precedence constraints. So PIK is a binary variable, and PIK is equal to 1 if for tasks Ti and Tk, task Ti has to be performed before task Tk, and Pik is 0 if the task Tk has to be performed before task Ti. Delta Ij is the variable that represents the time for completion of a task. So basically, if an agent J takes some time, delta Ij, to perform the task Ti, then delta Ij is defined. The workload variable Wij basically refers to the workload for an agent Aj to perform a specific task Ti. The Dik is a binary variable that is used to represent simultaneous execution. Basically, if Dik is equal to 1, then that means Ti and Tk are two tasks which are too close in proximity to be executed simultaneously. So that means the agents cannot execute the tasks Ti and Tk if Dik is equal to 1 because of the close proximity. And the proximity is determined using the Euclidean distance that is the second norm in R3. G of Ti basically is used for clustering tasks together. So if we pick a task Ti, then G of Ti will give us all of the tasks belonging to the set T, which come under the same category or are closely related to each other. So let's take a deeper look into the task features. So completion of tasks usually requires a minimum amount of accuracy, and the accuracy can be represented using this variable Qij, which can be any number between 0 and 1, and Qij is defined for all tasks Ti belonging to T and agents Aj belonging to A. So for a specific agent Aj, the quality of them or the accuracy of them while performing the task is represented by Qij, where 0 is complete inaccuracy and 1 is perfect accuracy. Since we learned about the G of Ti, which combines several similar tasks together, if for two tasks Ti, Tk, which are in the same category, or basically if G of Ti is equal to G of Tk for all Ti and Tk belonging to T, then for these two tasks, Qij is always equal to Qkj, which means the accuracy of the agent to perform task Ti will definitely be the same when the agent Aj is performing the task Tk. We did talk about the supervision of human beings. So when the human being, even the human agent supervises the robot. So the supervision quality QSIJ belongs to 0, 1 for all TI belonging to T and for all AJ belonging to A, which means obviously in this situation, AJ is the human being and not a robot, because only human beings can supervise robotic agents. So for a human agent AJ, given a task Ti, the supervision quality QIJS or QSIJ is determined to be somewhere between 0 to 1, where 0 is complete, like very bad supervision, and 1 is very good supervision. And the accuracy basically is very high because of that. Similar analogy to the previous statement we made, if two tasks come under the same category where g of ti is equal to g of tk, then the supervision accuracy or the supervision quality by the human being for both of the tasks will remain the same. So certain tasks do need collaboration, and we're going to use this variable ci that which is a binary variable to represent if the task Ti requires the collaboration between two robots or not. So if Ci is equal to 1, then the collaboration is needed. If Ci is equal to 0, then collaboration is not needed for this task. Certain tasks can only be done by or performed by human beings or robots. For example, if lifting an extremely heavy object can only be performed by a robot, whereas something that requires very good logical reasoning or very fine-tuned manipulation skills could be done by a human preferably. So in situations like these, the delta ij variable, which corresponds to the time to perform the task I by the agent j, is extremely high, is equal to m, where m is an extremely high arbitrary number. This is when agent is like either a human or a robot, and the task is not supposed to be performed by them. Then delta ij is going to be a very huge number. Similarly, the workload wij is also going to be a huge arbitrary number for a given agent aj when they're trying to perform task ti, when they're not supposed to do that because it's not meant for them. And of course, in this situation, all tasks Ti belong to T/Tj.
So let's dive into the problem. First, let's introduce the two binary decision variables. Xij is the binary decision variable for the assignment of task Ti to agent Aj. This means if the agent has to execute the task, Xij equals 1. Otherwise, Xij equals 0. Similarly, Sij is a binary decision variable for the supervision of the task by the human agent. If Sij equals 1, this means that the human has to supervise the execution of the task Ti. Sij equals 0 otherwise. The objective is to define the tasks assigned to each agent and the respective starting and end times, as well as the supervision assignments, by minimizing a cost function while complying with the system constraints. Here is the full mixed integer linear programming problem outlined. There is an objective with 10 constraints. Let's go through this in detail. The goal of this objective function is to minimize the system make span, which is the overall execution time, normalized with respect to the maximum execution time, Tm, while maximizing the overall process quality, given by the cumulative quality of each task, and minimizing the overall agent's workload. The quality values at the allocation time are considered, and the supervision quality and workload by human operators are also taken into account. So this is the first constraint. Xij, the sum of Xij over Aj in the set of agents equals 1 plus Ci. for all ti in t. So that's all for each task in the set of tasks. So this constraint ensures that the exact number of agents is allocated to each task. So for each task, a total of 1 or 2 agents must execute it depending on whether the task is collaborative, so that's a 1-agent case, or not, so that's a 2-agent case. Constraint 2 imposes a mutual exclusivity for supervision and execution by human operators. This means that for each task a human agent has, they cannot simultaneously execute it and supervise it. So Xij and Sij cannot both be 1. Constraint 3 ensures that no supervision can be performed by robotic agents. So in this equation, AR is a set of all the set of all robotic agents, and no supervision can be performed by robots, so only for the humans in the experiment. This next constraint implies that a minimum quality queue is guaranteed for each task. And the overall quality takes into account both the execution quality indices, Qij of the assigned agents with Xij equals 1, and the supervision quality indices for the assigned human supervisors with Sij equal to 1. So this inequality defines the minimum duration of each task. So that is, if the task Ti is assigned to agent Aj, Xij equals 1, then the allocation time must be at least equal to delta Ij. So delta Ij is the execution time required by the agent to perform the task. Constraint 6 imposes a precedence constraint. In this inequality, Pik is a binary variable. So for each pair of tasks Ti, Tk in T, if Pik equals 1, then Tk has to start after Ti ends, while if Pik equals 0, no precedence is imposed. These two constraints ensure that each agent Aj in the set of agents cannot simultaneously execute or supervise more than one task. So in these inequalities, Vikj is a auxiliary binary variable, and it allocates at most one task to each agent at each time. So what happens when Xij equals Xkj equals 1? Well, then we get 2 minus 1 minus 1, which is 2 minus 2, which is 0. And then by constraint 2 earlier that we saw, if Xij equals 1, then Sij equals 0. Similarly, if Xkj equals 1, then Skj equals 0, which means that this entire part of the equation goes away. 2 minus Xij minus Xkj minus both the S constraints becomes 0. And same thing with constraint 8. So those two constraints get simplified to these two inequalities. They imply that either Tk is greater than or equal to T if Vikj equals 0, but no simultaneous execution can occur. Similar reasoning is basically for the case in which Sij equals Skj equals 1. Finally, when the tasks are not assigned to the same robots, no constraints are imposed by the previous equations. So these two constraints allow us to specify that tasks that occupy the same spatial location are not executed simultaneously. Similarly to the constraints in the previous slide, there is an auxiliary decision binary variable, Zik. And that is a variable for spatial constraints. Based on this, if a spatial limitation exists between the tasks Ti and Tk, then the equations imply that Tk starts after Ti, that is Tk is greater than Ti when Zik equals 1, or the opposite holds true, that is when Zik equals 0. So note that the proposed formulation is particularly versatile and can be easily adapted to different collaborative production processes and tasks involving an arbitrary number of humans and robots.
So, what exactly is reallocation and why do we need reallocation? Due to the uncertainties in the real world and industrial settings in the real world, the reallocation of parameter values might be necessary to maintain optimality. So after the execution of each individual task, a monitoring step is performed to update these parameters, the four following parameters, that is quality, execution, time, and the workload. So initially, the parameter values are collected after the latest task execution. So if we focus on the quality, that is the supervision quality, or even the quality of the task performed by the agent. So it depends on a multiple number of factors. If the task was not supervised, then the measured quality will be equal to the current quality, and there will be no change in the quality whatsoever. If a task needed supervision, but the supervision did not include intervention by the human being, then the measured quality will be equal to the supervision quality, and the quality of the agent performing the task will not change. However, the supervision quality of the human being will be updated. If intervened while performing the task, then the measured quality is actually split or distributed between the human being and the robot agent in a new parameter set. Also, if two tasks Ti and Tk come under the same category such that G of Ti is equal to G of Tk, then the quality Q of K comma J will always be equal to Q of I comma J for all Tk belonging to tasks T, which means that if there's an agent Aj that performs two tasks Ti and Tk under the same category, then the updated quality will remain the same for all of these accuracy or quality values. For the workload and execution, these are just updated with the new values directly. However, the tasks lying within the same group are updated proportionally, which means that if the workload for a specific task was increased by 10%, then another task which lies in the same category will also see a 10% increment in the updation phase or of the parameter. So reallocation is basically done to ensure feasibility of allocation, which means since we just updated new parameter values, will the future task constraints be deviated or broken considering these new values? If yes, then reallocation is necessary. The second point is let's assume C plus to be the cost function of the future tasks that includes or takes into consideration the updated parameter values. And if we consider C cap plus to be the estimated cost function to perform the objective value given the previously performed tasks, then we need to let T plus be the subset of tasks that has to be executed, and in this scenario, and then the cap obviously represents the best estimate so far. In such situations, we will first find the C plus cap, which will then be used to find the dou value, and if the C plus cap minus C plus by C plus cap is greater than a small value delta t, then that means the cost function of in the future will be clearly needs a reallocation to be fixed. So because whatever cost function we have calculated so far is not going to be continued or followed in the future tasks because of the updation of the parameters. Thus, therefore, we'll need to reallocate a few tasks to different agents to make sure that the optimality is maintained. When a new batch of operations can be used and is available, reallocation should be done as well. The final situation where should be doing reallocation is when planned resources is not equal to the available resources, which means that maybe a specific human agent fell sick and is not available to work anymore, or a robot malfunctioned and is not able to perform tasks anymore. So the resource limitation requires us to perform a reallocation. So these are the situations in which reallocations should be done after the monitoring phase where the parameters get updated.
Now, let us detail the setup of the simulation. The setup is composed of two manipulators, so in the red boxes, and a human operator, which is in the blue box. Objects to assemble are numbered, and the desired structure is shown in the green box. The manipulators are Canova Jaco 2s and are mounted on sliding tracks. The left human hand of the simulated human operator is teleoperated in real time by a person through a Microsoft Xbox controller. Let's see how this works. Here is a diagram of the architecture of the validation setup. The human operator sends commands through a controller which is interfaced with MATLAB. The latter resorts to Gurobi Solver to find a solution for the optimization problem and communicates with VREP simulation environment. Visual feedback is provided to the human through VREP, which is shown right here. So the desired structure is as follows. We have 8 cubes that make up the base of the levels, so 4 cubes for each level, 2 planar surfaces, and 4 office items, a cup, headphones, keyboard, and a mouse, and they are added on top of the planar surfaces. A collaborative assembly process is considered in which a structure with 2 levels is built, as highlighted by the green dash box. Objects 5 and 10, as shown in the red box, are too large, so they need to be transported in collaboration. So in terms of the equations, C5 equals C10 equals 1, and that sets the respective task for 5 and 10 as collaborative. So precedence constraints are introduced to properly build the 2-level structure. Tasks 1 through 4 which position the cubic bases for the bottom level, need to be completed in order to start task 10, which positions the bottom planar surface. The latter task then needs to be finished to position the cubic bases for the top level. So that's 6, 7, 8, and 9, as well as the office items 11 and 12. After those tasks are accomplished, the top planar surface can be placed, and that is task 5. Finally, when the planar surface is mounted, the remaining 2 office items, tasks 13 and 14, can be placed. So execution times for the robotic agents are computed by considering the average linear velocity, which is equal to 0.05 meters per second, and average angular velocity equal to 1.3 radians per second. Execution times for the human agent are set by recording once the required times for the human operator to perform these tasks, and then we're multiplying these times by a factor greater than 1. So in this case, they picked 1.1 in order to obtain more conservative estimates. The resulting maximum execution time is 668.37 seconds. Finally, workload of the robotic agents is initialized to 0.5 for tasks associated with the first group of objects, so that is for the cubic base of the structure, while it is set equal to 1 for the remaining tasks. For the human agent, unit workload is considered for executing and supervising tasks associated with groups 1 and 3. High execution workload is considered instead to perform the collaborative tasks 5 and 10.
Now to see some experimental results. As we can see in this situation, three different robotic agents, A1, A2, and A3 were taken. And at the task allocation optimization based framework was used on them where over time. So as we can see for agent 1, initially task 4 was allocated to them, and then which eventually shifted to task 3, 10, 9, and 8 respectively. And this continued, the time taken to perform tasks 4 till task 8 for agent 1 was approximately 250 seconds. And after that, there was no task to be allocated to agent 1 for about 100 seconds, and then task 5 was allocated eventually. So for agent 2, as we can see, task 10 was also allocated to agent 2, and the robots agent 1 and agent 2 collaborated with each other to perform task 10 from t is equal to 80 seconds to t is equal to approximately 150 seconds. And similarly, task 5 was also shared between the two agents where they collaborated at t is equal to 350 to 3t is equal to 400. And eventually, like this resulted in two instances of collaboration between agents A1 and A2. Agent 3 was the only agent that needed human supervision, which is represented by the dotted lines, which means that the robot did complete the tasks or was allocated a specific task and it finished it, but uh, it underwent human supervision with or without intervention from the human being in the process. So as we can see, Agent 2 and Agent 3 collaborated with each other. However, Agent 2 was able to perform task 2 autonomously without any supervision, whereas Agent 3 needed the supervision uh, to, to aid its successful operation. The same thing applies to task 1 as well, and task 6 and task 7. So as we can see, there are 4 instances where Agent 2 and 3 collaborated, and in all of these instances, Agent 2 and Agent 3 needed supervision from the human being with or without intervention for a successful operation. And this basically resulted in a successful shared allocation between human beings and robots in an industrial setting. The advantage of reallocation can be clearly seen through this graph where the dou is basically the C plus minus C cap by C plus, which refers to the which highlights the difference of the cost function for the future plans given the updated parameter values compared to the cost function without the updated parameter values. So, and as we can see, if we do not use reallocation, then the value of dou increases over time for all the tasks t, and then which eventually resulted in a huge difference in the cost functions. But whereas with the reallocation strategy, the future cost functions were no longer heavily different or heavily contrasting compared to the current cost function because of the reallocation process, and that actually resulted in a higher efficiency and a higher rate of success.
In this work, the task allocation problem in a human multi-robot collaborative scenario was addressed. A general framework was proposed that allows to obtain optimal allocation considering several aspects like execution quality and workload, cooperative tasks, human supervision, and spatial constraints. The problem is formulated as a mixed integer linear programming problem, and an optimal allocation is found. Reallocation is obtained via real-time monitoring of execution parameters, and when performance falls below a given threshold, a new plan is computed. Further work aims at validating the solution in a real scenario, as well as defining an adaptive procedure to determine the threshold delta t for online reallocation according to human preferences. Thank you so much for listening.